Mm, This is 180949 presenting the MES lab task that is assigned to me. So here we have the first code for blinking the LED. This code is written in C language. So here are some libraries that are included. The DDRB is the direction port which is set so that the LED can be whether on or off. Here the port is directed set high DDB5, that is the 6th bit, or the PB5 port that is set high. Here is a loop while one port P is high, so that the LED is on for 1 second. Here we have the delay of 1000 millisecond, that means 1 second, and after that 1 second the port B gets low, so the LED is then turned off for a delay of 1000 milliseconds, and then the loop starts. Now we have the same code, but this time we are having this in assembly language. This thing tells the instruction to be written or to be placed in the Arduino board. Here is the R jump main. That means the code is jumping towards the main function that is mentioned here. The main code starts from here. LDI R16 mean we are loading the value in register 16, that is 0 cross FF. That means we are setting register 16 to high, and we are taking the out from register 16 in port B. So in register B, sorry. Now we have a loop here. The loop represent SBI and CBI. SBI means we are setting the port B, the fifth bit in the port B, and R called delay, and the CBI means the clear bit. That means the port 5, the port B at fifth bit, which is setted earlier, is now cleared, and then a delay. Now the delay loop is explained further below. Here is the delay loop LDR16. We are loading the value of register R16, and the outer loop where we are loading the values in R register 24 and register 25 as low and high respectively. And that BR any delay loop means it's a conditional loop. When the loop is completed, it goes back. And for the Proteus simulations, we have the file here. I will upload the file here. Now you can see that the LED remains on for a second and then turns off for a second. Now moving towards the lab 2. In this lab, we have to just simply take input from one port and display it on the other. Here we have the code here. In this, we are loading the values in register 16 and register 17. We are taking register 17 as input and 16 as input and 17 as output. Whether we are directing the port B to R16, which is taken as input, and RC at 17, which is taken as output. So here we have the loop in which we are storing the values in R18 which is directed to pin B, and we are taking that output from port C at R18. And jump means the here is the loop which is going on and on. Here we have the circuit in which we have different combinations. If I open them, some of them, we can see that the first is closed, so the light is on, then the second is off, and so on. Now the task 3 is that we have to create a charging style LED in which we have loading the values at the register R16. We are taking the R19 as high and taking the output from port B. Here is a loop L3 in which we are setting the values of 0 bits on port B, 1, call the delay function, and then clearing the bit that is stored. Then we call the delay function again. Same is the case, and but now the 0, first we have set the 0 bit high, now we are setting the first bit high, then call a delay function and then clearing the bit. Same goes on and on until the fifth bit clears, and R jump L3 means the loop is then shifted again here at L3 and it starts again. Here is the delay function explained. We are loading the values in these three registers, and the here is we are uploading garbage's value for some delay and the decrement. Here is the Proteus. The file is already uploaded. Here you can see that the charging pattern is obtained. Now moving towards the task 4 in which we have to take input from two ports and output from one port. You can see that we are taking register 20 and 21 as inputs, B and the port B and C as input, which are referring to R20 and R21, and the port D refers to R25 that is set at high. That means we are taking output from port. Here we are loading the values in register 22 and 16. And the loop here is R17 pin C and R18 pin B. This is the input, and we are subtracting R17 from R18 and the result is stored in R17. Now here is the output at port D which refers to R16. Now the next is defined here is port D is uh, set to register R22 and then it jumps to L1 where L1 is this and the loop is going on and on again. Is the Proteus where we can see that if both the switches are open, all the LEDs are on, and if one of them is closed, the LEDs will get zero values and will be off. Now in lab 7, we have to make a counter that starts from 0 and goes up to 99 by using two 7-segment displays. Here we are defining the LED direction LED ports. We are using the name LED direction and LED direction 1 and similarly port and port 1. Here we are making a character array that is in hexadecimal because we are taking input from hex keypad, that is the hexadecimal input. For the counter, we are initializing a loop that turns from 0 to 10, and in that loop we are adding another loop. So the first one is initializing with j and the second is with the variable I. The inner loop starts from 0 to 10, and when it reaches 10, it goes out to the outer loop, that is j, and it repeats itself. I plus plus is the loop, and the LED port is initialized with array I that is defined here, which shows the characters from 0 to 10, and then it goes back to the outer loop and adds 1 in it. Is the Proteus simulation. You see that when it reaches 9 and it adds 1 in the previous 7 segment display. So it's 1 added to it and now it's 2. The second task is that we have to use a hex keypad and turn on the LEDs. For this, we are using the loop simulation. We can either check the column or the rows. Here we are checking the columns. If pin D is this, now the right sides are the rows, right 4 bits are the rows, and the left 4 bits are the columns. So we are checking the C1, column 1. If the input is 1 here, the loop will break and the respective LED will on. If not, it will go to the else if loop, and similarly it goes on and on for the 0, 1, 2 and third bit of the column 1. Same is with the column 2. Here we are checking that if the LED, if the button is pressed, the 0, 1 and 2, 3 bits check are checked. If any of them is high, the loop will be terminated and goes back. Same is the case with column 3 and column 4. Now it's the main function. Here we are defining the direction of the port B and port D. The port B is the output port and port D is the input port that is defined here. Now we are here. I already uploaded the hex file. Here press this first. The C4 is pressed, so the LED on the column 4 is on. Similarly, if C2 is pressed, so to restart the simulations, there is a issue with the ground that if it is high, it will remain high, and you can see that this is the type. Thank you. Now in lab 4, we have to just display some characters on LCD. We just need to interface with the LCD and know how to use an LCD and its pin. It's just a simple code. We are in a loop. LCD INIT is the function that we are calling here, and the LCD display function in which we are writing hello world with a delay of 500 milliseconds, and then the LCD will clear. Same, we are using the three inputs, hello world, and then we are displaying temperature, and then we are displaying the day of weather of the day, each having a delay of 500 milliseconds. Here we are calling some functions like delay function, display function, that is already been stored in the LCD function, LCD header file. Here we have the Proteus simulation. I already uploaded the code. You can see that it is printing hello world, temperature, and the weather of the day. Now in lab number 5, we have to make a digital clock. In this, we are including the LCD header file, and then we are defining the data port as port D and unsigned int for displaying hour, minute, second, and a check. Now the data is displayed on the LED, so we have to make a variable LCD clock where we are assigning it int A and unsigned int A and unsigned int B. Here is a loop. If A is equal to 0, the LCD will write start from 0, and that is a colon. And if A is not equal to 0, here are some steps to convert the numbers in hex. Now we are initializing the timer 1, TCCR1B. We are initializing the timer in CTC mode with no prescaling. Now we are initializing the timer 1 interrupt with a global interrupt SEI and a timer register or timer mask. Now this is the main function where we are checking the what to display. Here we are making a variable check plus plus. If check is equal to 0, a second is plus in it. When the second reaches to 59, second will again go to 0 and a minute is plus. Same goes with the minutes. When the minutes goes to 59, the minute clock will go to 0 and 1 hour is plus in it. And when 24 hours are complete, the clock will reset to its 00 position. And here are some delaying function, and the address is to display second where the second will show and so on. I already uploaded the X file. Here you can see there are seconds counting on from 0 to up to so on. Now moving towards the timer, in which we have to display some connectors on LCD. Here we are adding the LCD file. Here we are using the timer in CTC mode, and here we are giving it a binary input. initializing TC and T1 is equal to 0 and OCR is equal to 1. We are defining two data types, int and character. I1 is equal to 1 and I2. Now we have in this step the timer 1 is to roll over and I2 means how many digits are being displayed, and LCD display to I1 plus plus means that int there is an increment in int where we define int as 1, so it will go on like 1 2 3 4. Now the LCD will clear, and this is and the kind of produce simulation like it's going on 1 2 3 4 5 6. Lab number 6, we have to communicate between two microcontrollers. In this specific lab, we have to communicate in two specific microcontrollers and display some digits, taking some input from X keyboard and displaying it on the other by using two microcontrollers. We are doing this in three protocols: SPI, UART, and I2C. Here I am defining the SPI. We have two microcontrollers, the master one and the slave one. Here is the code for the master one, in which we are defining the MOSI, like MOSI is master out slave in, and MES is master in slave out. We are defining these both. Now we have to send data on the master. Here the master is taking input from the hex keypad, which is defined as 789, and divide this specific array is created on the basis of hex keypad, as the hex keypad looks like this, and we have a character from A1, A2, A3, A4. These are the rows and column lines that are being checked. Here we are setting that what is pressed on the hex keypad. R1 is the row 1 and C1 is the column 1. If these both are 0 and x 0, now the main function consists of the master. Now we are referring the direction of port D as 0 cross F0, and port D itself is 0 cross 0F. Now we are reading the input from port D. The input is coming from the X keypad onto the port D. If X is not equal to 0 cross 0F, the function will break and go back to the original position. Port D is equal to 0 cross EF. Now EF is the hexadecimal number which is coming from the X keypad. If it is not 0 cross F, R1 is equal to 0 and the search function is again implemented. Now moving on, port D, 0 cross DEF is another hexadecimal number which consists of 0, 0, 1, 0, 1 if I convert it into binary. So 0101, it's like binary numbers and have special meanings. Each individual does the same goes on to the whole circuit. Now the void search function is defined. If x is equal to 0 cross 0 e, the A1 database is printed. Like the A1 database is the row 1 and the 0 means the 0 of the LCD, and send data means the data is sent to A1 with a delay of 100 milliseconds. Same is the case with A2, A3 and A4. Now we send the data to port B where it is transferred from master to the slave, and we are getting the Mozi and Mizo and SS pin and all set into the high position. Now moving toward the slave which is receiving information from the master and displaying it on the LCD. Here we are including LCD for SPI function library, sorry. Now we are considering Mizo master in slave out. At the first we are taking it master out slave in. Now we are getting the master in slave out as the second microcontroller is taking input from the master and the slave is doing the output function to the LCD. Here we have the while loop and the LCD data write which is received from the master. The slave writes it on the LCD. The broadcast simulation is here. I already uploaded the X files here. So when the LCD is on, we can see that when the 7 is pressed, 7 is displayed here. When 5 is pressed, the 5 is displayed here, or any number is displayed. We can see that on the LCD. Mm. Now in lab 7, we have to do to show some data on the LCD. Basically, it's the interrupt function that we have to call. Here is the LCD header file. The actual main code is here. We are taking DDRC as output and DDRB as input. 0 cross FF means we are taking output as high, and 0 cross 07 means the first 3 bits we are taking high for the RS, RW and E. Now taking the DDRD as input from pin PD2 and PD3. Here we have EIC R1, that is the trigger to any logic state. We are using two interrupts, ISC0 and ISC1, and here we have EIMSK, that is the interrupt mask for the int0 and int1. And now we have the global interrupts. Afterwards we have a loop. While one we are calling the LCD function and a delay. Now we are sending data to the LCD by using LCD data string. Here we are defining the interrupt function int0 and int1. If If this function is called, the screen is first clear and then the data is showed as interrupt 0. Same is the case with the interrupt 1. Here is the Proteus simulation. Now you can see that the data is printed on the LCD. If I press this, the interrupt 0 is called, and for this interrupt 1 is called. Moving towards the lab 8, which is basically the ADC lab. Here we have the main file of ADC, in which we are calling the LCD function and DDRC as input 0 cross 0 0. We are selecting the channel from AD mux with AVCC external capacitor and enabling the ADC with enable interrupt and clock. First we display temperature on the LED. Now we have to convert the data taken from the sensor and displayed on the LCD. Here is the converting factor. This is the function which is used to complete the conversion. When the function is converted, the whole ADI flag is cleared. Now this is the LED set cursor from where the LCD will start to display, and LCD display value, the value is that is converted up here, and then Celsius is written in front of it. Here is the Proteus simulation. I already uploaded the code here. We can see that when 27 is here, the LCD is showing 27, and if I add 1 in it, it's add 1 in it. Now moving towards the lab 9, which is the brightness controlled LED. Here we have a duty cycle thing. We, we are using the fast PWM mode for the control of LED's brightness. TCCR0A is the timer counter register and TIM is the timer mask register. OCR0A, we are calculating the OCR0A by using the duty cycle divided by 100 and multiplied by 255. SCI is the global status enable interrupt. Now we are using the delay function, and duty cycle plus is equal to 10 means the brightness is incremented with a 10% each time it is displayed. Now here is the loop. If duty cycle reaches 100, the LED will turn off and go back to its original position. But that loop will not turn off the LED. It is like duty cycle minus is equal to 50 in 2 steps. The LED will turn off in 2 steps, and when duty cycle is equal to 0, the loop will break here and go back to its original position where it starts to glow again in with the increment of 10. Here is the interrupt function ISR, in which the duty cycle is calculated, that is calculated above, and OCR0 is shown here. Here is the Proteus simulation. Already uploaded the code here. Now you can see that the light is blinking, but the thing is that we can't see the brightness increment in Proteus. However, we can see that in the hardware. is all from the lab 9.